Is it only going to be the three of us today? I guess there's a job fair going on or something now, right? So
Unless they're in the Thursdays Zoom lecture waiting on us.
yeah, that could be.
Yeah, I
You
don't
know,
know.
I don't know. I've maybe it would be easier if I just used a recurring event with the same. Yeah, I usually get a notification if somebody's waiting for me in a Zoom meeting that I'm running, and I got the notice when Elijah logged on, but that was it. So yeah, I wouldn't be shocked if they're at the job fair now, and then that's going on all week this week, right? I can
Honestly, I don't know. I only attended freshman year, so that was it.
September 12th through the 14th. Yeah, professional and technical career fair. So, all right. Well, we'll get going anyways. So I'm yeah, there we go. Sharing again from my office. Um on campus. I've got a contractor working at home today on the bathroom, and so they're probably making more noise there than I would have in my office here. So I decided to come teach from here. Um, so today's lecture, we're going to talk about matrix analysis. But before we get into that, let me just give a couple of slides showing my schedule for the week. My office hours are tomorrow from 1:30 to 2:30. And then again on Thursday from 8:30 to 10 via Zoom. So I'll be available during those times, or feel free to drop me a text message and let me know if you need to meet with me at any other time. Still no teaching assistant for the class, so I presume that I'm going to have to grade your assignments. I know you have one that was submitted last week, so I'll find some time to look through that here in the next couple of days so you guys get some feedback on that. Homework number 2 is due this afternoon at 5 o'clock. And then homework number 3, I haven't assigned it yet, but it's going to build off of today's lecture, and then I'll make that due next week sometime. Probably not Tuesday, probably Wednesday or Thursday, to give you a couple extra days to ask some questions on that. Anybody have any questions on homework number 2 before we get going? That's most of you should be well along your way to having that complete. If you're not, then you're probably planning on spending the rest of the afternoon working on it, I would presume. So I had a couple of questions over the weekend, tried to field those as they came in, but I don't think any of them rise to the level of spending time in class talking about them. All right, then. Hearing none, then let's go ahead and move on to the next presentation. And so I have a series of 5 or 6 different analysis lectures that I worked through. And the way that these are structured is that the first 2 kind of go together. I have it broken down into lecture 1 and lecture 2, but after lecture 1, you still don't quite know enough to do anything. So we're going to try and work through both of these lectures and see how far we get today. This is a little bit on the technical side. So if you're somebody who didn't like the linear algebra classes that you've taken, or the matrix analysis operations, this is probably going to be the least entertaining or the least interesting part of the class for you. But I think that going through this material and understanding how the matrix operations are performed behind the scenes makes you a better user of the software in the end. So even if you don't do the matrix operations when you use SAP 2000 or visual analysis, understanding what's going on behind the scenes will make you a better user of the software in the end. So that's why we go through this. All right, so everybody probably remembers the spring system that we taught in physics, or that you were taught in physics. And so the idea is, if you have a spring with some known stiffness, you can apply a load to it, you get some displacement X. If you apply the 2 times the load, you get 2 times the stiffness X. And so we can write the relationship that K times X is equal to P, or K times delta is equal to P. And in that relationship, K is the stiffness of the spring, X or delta is the displacement that results, and P is the amount of force or the load that's on that. So what we're going to do basically is we're going to expand on that single degree of freedom system, one value for delta, and we're going to expand it into a multiple degree of freedom system that is more usable for us in structural analysis. So we're going to rewrite that equation, K times delta equals P, in the form of a matrix or in the form of matrices. And we end up with a stiffness matrix K times some displacement vector delta is equal to a vector of loads P. And so in that equation, K is the structure stiffness matrix, and I'm careful to define it here as the global stiffness matrix. Delta is a matrix of displacements that the structure will undergo due to externally applied loads, and the P vector is the externally applied loads that are on the structure. So I'm careful here in calling out my notation. We're going to introduce another value of K in a minute that's K sub I, and that's a stiffness matrix associated with a specific member within the structure. And that's different than the structure stiffness matrix. So the notation gets to be a bit tedious here. So K is different than K sub I, and I just want to call that out to you so to hopefully avoid a little bit of confusion. So basically the premise is that the displacements are the unknown quantities. And so if we know what the stiffness matrix is, then we know what K is, and if we know what the loads are that are applied to the structure, then we can solve a system of equations to determine what delta is. And basically in matrix operations, we would invert K, multiply K inverse times the load matrix P, and that would give us the displacement vector delta. And overall, the goal is to develop a set of simultaneous equations that can be solved for the unknown displacements. And so this has its roots in linear algebra, and really it's ideal for a computer because computers are perfect at solving sets of simultaneous equations. That's one of the ideal solutions for a computer. And so if we can set up the problem, if we can structure the problem such that we get a system of equations, then the computer is an ideal tool to solve for that system of equations. All right, so some definitions. If we have a linear static analysis, that means the loads are static loads. We're not talking about dynamic loads like you might see in an earthquake. If everything is linear, where we're not having any yielding or any nonlinear behavior like that, then there is one global stiffness matrix for the whole structure. There's only one. There's not two. There's not zero. There's exactly one global stiffness matrix. The size of that matrix, I think you would call it the rank of the matrix if you were a math magician, is the number of structure degrees of freedom by the number of structure degrees of freedom. So the matrix has NSDOF columns and NSDOF rows. Actually, it's rows and then columns. And so if we look at the different types of structures that we can consider, for a plane truss, there's 2 degrees of freedom at every node. For a space truss, there's 3 degrees of freedom at every node. For a plane beam, there's 2 degrees of freedom for every node. There's 3 for a plane frame, and then there's 6 if we consider a space frame. And so the displacements, delta and P, they can be either vectors or matrices. And so the size of these matrices is the number of structure degrees of freedom for the rows, and the number of columns is equal to the number of load cases that we consider. So if we look at our homework number 2 that you guys are doing for your beam stuff, there's 3 service cases, and then there's some load combinations that go along with it. So for those 3 service cases, you would end up with 3 columns for your delta matrix and 3 columns for your load matrix P. All right. So let's go back to this truss that we were tinkering with last week, and we'll use this as an example. And what I'm going to do is set this up as an example problem to illustrate the direct stiffness method. And you guys probably saw this PDF of this uploaded to the Canvas site if you checked before class. So you guys can follow along on this, and it's also in the PowerPoint as well. So this is a bit more compact in this PDF, so you can work with that directly after you understand the concepts. All right, so for this particular truss, we have 5 nodes labeled 1 through 5. So if each node has 2 degrees of freedom, then we have 10 degrees of freedom total. And our global stiffness matrix, K, will be a 10 by 10 matrix. So we need to number the degrees of freedom somehow. So what we typically do when there's 2 degrees of freedom at each node is we label 1 degree of freedom 2 times I minus 1, and the other degree of freedom 2 times I, where I is the number of the node. And you guys went through this exercise as part of homework number 1, so hopefully this is old hat for you at this point. This is probably something you're familiar with. So for example, degree of freedom number 1 would be the displacement in the x direction at node number 1. So 2 times I is 2 times 1, minus 1 is 1. For example, degree of freedom number 8 is the y displacement at node number 4. 2 times 4 is 8. All right, so what we're going to do then is define what a stiffness coefficient is. One element of our stiffness matrix, K, is K sub ij. And so when I use that notation, K sub ij, I is the row number, J is the column number. So this is probably consistent with your math classes. So when we look at this, then we have the stiffness coefficient Kij defined as the force at the location and in the direction of the degree of freedom I that's required to cause a unit displacement at degree of freedom J, where all other displacements are taken as 0. So you could read that 5 times and still need to think about it some more. It's an involved definition, but maybe if we illustrate it here with some graphics, maybe that'll help. So if we impose a unit displacement that corresponds to the first degree of freedom, then that is the result. So basically, this is moving 1 unit to the right. So maybe that unit is inches, maybe that unit is millimeters. It doesn't matter. It just matters that you're consistent with your notation. So in order to do that, let me erase that so we don't get too busy. In order to impose that displacement, we need a force in that direction. So that force is the force that is in the one direction that is there to maintain a displacement in the one direction. So in this case, I is equal to 1 and J is equal to 1. But if we move that node to the right, we also need to provide a force that's vertical at that location. So that is F21. That's the force in the 2 direction that results or is needed to have a unit displacement corresponding to degree of freedom number 1 with all other degree of freedoms held 0. And then we could go on and we look at the opposite end of member A. We would need a force that acts to the left in order to keep that node from moving to the right. We would need a force that acts downwards to keep node 2 from moving upwards. And then at the opposite end of member B, you would need a force that acts to the left to keep node 3 from moving as well. So if we move node number 1 unit to the right, if we impose a displacement of 1 unit corresponding to degree of freedom number 1, we need 1, 2, 3, 4, 5 forces in order to maintain that displaced equilibrium of that structure. And so those 5 forces represent the non-zero elements of the stiffness matrix that would be in the ith column, right? So Kij, I is the J is the first column, so we would have several elements within that first column. Then in theory, we could go on and do that again. In this case, let me skip to degree of freedom number 4. We'll impose a unit displacement that corresponds to degree of freedom number 4. Obviously, we need a force to make that happen. So that is the force F44. If we move that degree of freedom upwards, we're also going to need a force acting to the left to keep that from moving left to right. So we have a force there that is F34. We're going to need forces at node number 1 to keep node 1 from moving. We're going to need forces at node number 3 to keep node 3 from moving. And we're going to need forces at node number 4 to keep node 4 from moving. Note that we don't need any forces down here at node 5 because neither member F nor G have stretched at all or have been compressed at all. So there's no force required to hold node 5 from moving when we impose a unit displacement at node 4 in the vertical direction. All right, let's do one more. If we look here at node number 3 in the vertical direction, See, 2 times 3 is 6. So that would be a unit displacement in the 6th degree of freedom. Then we would obviously need a force acting upwards to impose that. We could possibly need a force acting to the right or to the left to keep it from moving to the right or to the left, depending on symmetry of the structure. We're going to need forces acting downwards at nodes 2 and 4, and we're going to need forces acting to the right at node 2 and to the left at node 4 in order to maintain that equilibrium position. And then finally, we need 2 forces acting at node 1 and 2 forces acting at node 5. So every time we impose a unit displacement like this that corresponds to one of the degrees of freedom, we could basically use our structural analysis to derive each of the forces that's necessary to hold that displaced equilibrium. And in so doing, we would be calculating the stiffness coefficients that correspond to one column within our stiffness matrix. All right, I think I've got one more in here, but this is getting just a little bit tedious at this point. So a displacement corresponding to degree of freedom 9, we would need F9, 9 there. We would need a force acting downwards, F10, 9. Then we would need forces at node 4 and then back here at node 3. All right, so if we were to calculate all those values, then what results is the first column of the stiffness matrix resulting from a displacement corresponding to degree of freedom 1 that equals 1 unit. When we displaced corresponding to degree of freedom number 4, we were calculating the coefficients that correspond to the 4th column of the stiffness matrix. We also did degree of freedom number 6, and then finally degree of freedom number 9. So those values of F that we could have calculated correspond to these different values in our stiffness matrix. All right, now some more properties of the stiffness matrix. Again, there's only one stiffness matrix for every structure. Oh, I'm sorry, I'm shifting gears a little bit. Let me go back. I thought I had something else coming up. One more characteristic of the stiffness matrix is that it's always symmetric as well. So if we look here, for example, you have a negative 348 for row 1, column 3. If we look at row 3, column 1, that value will be identical. If we look at, say, row 3, column 7, we get a value of negative 805. If we look at row 7, column 3, then you get the same value. So that stiffness matrix is always symmetric. Another characteristic of it is that none of the diagonal terms should be negative or 0. I didn't do a very good job of doing that. Let me grab a ruler here. So if we go through, I'll just draw a line through the values as opposed to trying to circle them. If we look at the diagonal terms of that stiffness matrix, they should all be non-zero and positive. All right. And if you have a 0 element on that diagonal, then that's going to lead to problems in the solution of your system of equations. All right. So that's the global stiffness matrix for the structure, K. And then now moving on to the next slide. For every structure, there's one element stiffness matrix for each element or each member within the structure. And so the element stiffness matrix has a notation K sub I, where now I is the member number that you're examining. So for the truss that we were looking at, there was 7 members, so there'd be 7 element stiffness matrices corresponding to those 7 members. Now for excuse me, for each one of these element stiffness matrices, the size is equal to the number of member degrees of freedom, and each of these matrices is also square. So NMDOF is the number of member degrees of freedom. And so if we go back and look at a plane truss, there's 2 degrees of freedom at each end of a truss element or each end of a truss member. So that means that we have 4 total degrees of freedom for each truss member. So each truss member stiffness matrix, K sub I, will be a 4x4 matrix. If we go to the bottom, for each space frame member, we would have a 12x12 member stiffness matrix or element stiffness matrix. All right, now, right, K sub I is the element stiffness matrix in terms of the global coordinate system. And we also have delta sub I, that is a vector of element displacements in global coordinate systems. And then what I'll do is I'll bring in an element like this that has the forces outlined in there. So we have K sub I, we have delta sub I, and we have F sub I. So what's important is that we could recognize, and this is going to be the topic of a different lecture later on. Let me change color here in my ink. That there is a local coordinate system for each one of these elements as well. And so we have a capital X axis that is the global X coordinate system. We have a capital Y axis that's part of the global coordinate system, but we also have a lowercase x axis, a lowercase y axis that is the local coordinate system for each one of these members. And what's important is that when we have a capital K, that indicates that we have an element stiffness matrix in the global coordinate system. And later on, we'll introduce a lowercase k that is the element stiffness matrix written in local coordinates instead. And I think that that's the topic of the third lecture that I posted. I don't think we're going to get there today, but if you wanted to look ahead a little bit. There's also a local displacement vector delta, that's the displacements in the local coordinate system. And then there's a lowercase f that is the member end actions of the element in local coordinate system as well. All right, I'll just give you a little bit of foreshadowing there, tying into the idea of local versus global degrees of freedom that we discussed last week. And so if we look at this on an element by element basis, we come up with the same formulation that we had for the structure as well. So we had the structure stiffness matrix K times the structure displacements delta is equal to the externally applied loads P. But for each member within the structure, we can also write a similar relationship where K sub I times delta sub I is equal to F sub I. And then in this case, F sub I becomes the member end actions, and we can use those to calculate the forces that are in the member itself. So in the context of a truss member, we would be calculating axial force. In the context of a beam member, we would be calculating shear forces and bending moments. And that's what that value of F is. So the next trick then is, what is the element stiffness matrix K sub I for a truss element? And we can write it like this. So we have the term AE over L, which you guys will recognize as the axial stiffness for a member subjected to an axial force. And then we multiply by a 4x4 matrix of our directional cosines. So the 1,1 element is the cosine squared. The 2,2 element is the sine squared. And then we have the cosine of phi times the sine of phi, and the 1,2 and the 2,1 element. And so that's how you determine what these element stiffness matrices are, by using that formulation. Now, you'll note that there's two sets of repetition here. Number one, this matrix is symmetric like the global structures stiffness matrix is, but there's also some symmetry in that that block is equal to that block there, and then this block up here in the upper right is equal to this block down here in the lower left. So really, there's only four discrete values, well, maybe even 3 discrete values, not counting plus and minus signs that are in there. Okay, and then we can also stipulate what the displacements are. The value of delta sub I is given as delta x1, delta x2, delta y1, and delta y2. And then we have the forces fx1, fy1, fx2, fy2. And it strikes me that these should probably be the squiggly brackets here, because they're vectors as opposed to the square brackets that would represent a matrix. And so I should, to be consistent, I should probably represent them like that. But they can be matrices, but in general, we just say that they have one column generally. All right, and then to determine the element stiffness matrices, you can calculate the directional cosines. And I think I showed this slide as part of one of our introductory slideshows. So homework number 3 is going to involve going back to the truss that you looked at in homework number 1 and calculate the element stiffness matrices, and then assembling that into a global structure stiffness matrix, and then inverting and finding the displacements. And so you've already done the first part of that in calculating the directional cosines and the lengths of the members. And so you're not halfway done, but you're part of the way done with that. So to summarize, in the stiffness coefficient Kij is the force at degree of freedom I required to cause a unit displacement at degree of freedom J while holding all other degrees of freedom at 0. And some other properties here, the stiffness matrix is always symmetric, and for a 2D truss element, this is our element stiffness matrix. And so you can write it a couple of different ways. I've got it written AE over L times the 4x4 matrix of directional cosines, and then you could also write it with K11, K12, K13, etc. All right, now to determine these element stiffness matrix, we go back and use the same approach that I illustrated before. And what I'm going to do is impose a unit displacement that corresponds to each of the 4 degrees of freedom for the member. And when I do that, I'm going to need forces that are required to hold each one of those degrees of freedom at its displaced magnitude or its displaced location. So if I move that degree of freedom to 1 to the right at delta x at the first node, then I'm going to need forces that correspond to that. So let me go back to red. So I'm going to need a force here. I'm going to need a force there. I'm going to need a force up here, and I'm going to need a force like that. And so this is going to be the force in the 1-1 direction. This is going to be the force in the 2 direction resulting from a 1 degree of freedom displacement. This is the force in the 3 direction corresponding to a 1. And this is a force in the 4 direction corresponding to a displacement in the 1 degree of freedom. And so basically what I've done is I've derived the first column in that stiffness matrix. And so note that for the row 3, column 1 element, it's actually negative. And that corresponds to this force pointing to the left, right? It points in the opposite of positive, so it's a negative value, and that makes sense. The row 4, column 1 element is also negative, and that corresponds to this guy here pointing downwards instead of pointing upwards in the positive y direction. All right, and so note that we have an axial deformation delta that is different than the capital delta x sub 1. And so what we had to do was correlate the axial shortening of this member to the horizontal and vertical displacements that relate to the global degrees of freedom. And then we could do the same thing again. In this case, I'll impose a displacement that corresponds to the 2nd degree of freedom, delta y at node 1. And again, we're going to need some force here. I don't know why it keeps erasing like that. I think it's because I have my palm on the surface. So we need a force that goes like that. I just can't make it work. Let me do this. Try starting it again. Okay. So we're going to need a force that looks like that. Nope, it just won't work. We're going to need a force that goes upward as well. Right, you thought I was going to write something else, didn't you? No, not going to do that. Not while I'm being recorded. Okay, so we need a force F11. I just can't make it go that way. I don't know why it won't work. Right, okay. And so when we solve for those forces, basically we're solving for the elements that are in the 2nd column of this matrix. Actually, the first force would actually go to the right, so it still won't let me draw it in there. But then we could go through and do the same thing for the 3rd degree of freedom. We would develop the forces that correspond to the 3rd column in our stiffness matrix. And then finally, we could do it for the 4th degree of freedom as well. And those 4 forces would correspond to the 4th column in our stiffness matrix. So it's, the first time you do anything is challenging, but calculating these values of the stiffness matrix. The calculating the stiffness coefficients for a truss element is rather rudimentary. You're just taking an axial force or an axial member, and you're either stretching it or you're compressing it. So most of it is associated with the geometry at the ends and making sure that even though you're stretching the member at some odd angle phi, that the forces at the ends are either horizontal or vertical, so they correspond with the global degrees of freedom or the global coordinate system. So most of the problem here is a geometric one. So if we apply this process to our example truss with 5 nodes and 7 members, there should be 7 element stiffness matrices. So what we're going to have is 1 element stiffness matrix for each of the members, A through G, and we could go through and write those out like this. So we have 1, 2, 3, and 4 there for A, B, C, and D. And then we can go through and here we have E, F, and G as well. So if you go and look at the example problem that I posted, the first step was to compute the member connectivity. So member A goes from node 1 to node 2. Member D goes from node 2 to node 4 For example, here are the nodal coordinates, the x coordinate of the ith node, the y coordinate of the ith node, the x coordinate of the jth node, the y coordinate of the jth node. Here's the length L, and then here are the directional cosines. And so you just go through with a spreadsheet and calculate those out. Then the next step is to label the degrees of freedom. So here's just like a decoder wheel, if you will, or a rubric or a matrix that shows what the degrees of freedom are for each of the nodes. So for member A, for example, it connects node 1 to node 2. So we have degrees of freedom associated with that member are 1, 2, 3, and 4. So member A is right here, and we have degrees of freedom 1 and 2 at its first end and degrees of freedom 3 and 4 at its second end. If we look at member D, for example, it connects nodes 2 and 4. And so the degrees of freedom at the first end are 3 and 4. The degrees of freedom at the second end are 7 and 8. All right, and then finally on page 3, I go through and I calculate the stiffness matrices for each one of the 7 elements that are in the structure. Now, if we go and look at the spreadsheet that's behind this, it's formatted a little bit differently. So this is my element stiffness matrix calculation. So in here, I'm just basically entering in the area of the member, the modulus of elasticity of the member. Here is the x location of the ith node, the y location of the ith node, the x location of the jth node, the y location of the jth node. And then here, wherever there's an equal sign, that's something that's calculated. So I'm calculating the length at 240 inches, calculate the cosine of phi, the sine of phi. And then over here in my stiffness matrix, I'm just calculating the AE over L, and in this case, multiplying by cosine squared. If I go down here to the 2, element of that matrix, then I have AE over L again multiplied by the sine squared. And so this is not very complicated. It's simple math. But it can be challenging because it's easy to screw up the indices and put the wrong element in the wrong space. And then what you'll see here is that I'm labeling my rows and columns of each one of these member stiffness matrices that correspond to the global degrees of freedom. So for example, let me alt tab back over here, go back a couple of slides. Right, member A connects degrees of freedom 1, 2 to 3 and 4. So here we have degrees of freedom 1, 2, and 3 and 4. If we look at member D, for example, let me actually go back to an earlier version. Here we go. So if we look at member D, it's connecting degrees of freedom 3 and 4 at its ith end to degrees of freedom 7 and 8 at its jth end. So if we look here, we have 3 and 4 connecting degrees of freedom 7 and 8, and then we have rows 3, 4, 7, and 8. So that's how this is all laid out. And so when you guys go through and do homework number 3, I expect you'll lay out your spreadsheet in a way similar to this. Now, I get a little anal retentive about this. I actually have a column here that represents the the brackets to each side of that. I've gotten to the point where I usually just put a vertical line on that now, so that's a little bit superfluous when it comes to the math. It's certainly not required. Right, and so there's 7 of these guys that are broken out, and there's some extra math here, but we haven't gotten far enough to explain all of that yet. All right, let's go back to PowerPoint and pick up where we were. Right, and so we have those 4 stiffness matrices, those 3 stiffness matrices, so we have 7 matrices total. Now, after we go through and solve for the displacements delta, we can solve for the member end actions, or the member forces F, based on those displacements. And those member forces, there's 4 of them for each truss member. There's 6 of them for each 2D frame element. There's 12 of them for each 3D frame element. And basically what we do is we go through on an element by element basis, and we calculate those end actions by taking the member stiffness matrix times the displacements that we calculate. And then we can get those member end actions. And then we can go through and use equilibrium to relate the internal member force P to the external end actions. And so what we can do is solve for P. We could look at the second end of the member, and we could say that P is equal to Fx2 divided by the directional cosine. Or we could say that P is equal to minus Fx1 divided by the directional cosine. And that'll work in most cases, but there are cases where the cosine of phi is equal to 0, and that equation would blow up. So in those cases, we would have to use the second form of the equation, where P is also equal to Fy2 divided by the sine of phi, or minus Fy1 divided by the sine of phi. Right? And so through back substitution, we can find those member end actions, and that looks like this. And I think I have it in here for 2 of the members. And so what that does is that explains what's going on over here in column S and W. Now, in order to determine these, we actually have to go through and do our linear algebra. We actually have to solve a 10 by 10 set of equations in order to get these displacements. So I've skipped that step in this presentation. But once we know what those displacements are, then we can solve for our member end actions. And so if I go here and do a mouse over on this, you can see that P is just equal to negative W4 over E7, which is the Fx1 divided by the cosine of phi. Right. And occasionally, if we had a vertical member, there aren't any vertical members in this truss, so we don't have to worry about it here. But when you have a vertical member, then dividing by 0 is problematic. So, all right. So to close out this presentation, then what we do is present a step-by-step. You guys, students, all love just the step-by-step procedure as to what we're doing. So the first step is to identify and label each degree of freedom at each node. And then we need to formulate member element stiffness matrices case sub I. There'll be 1 for every member or every element in our structure. Then we need to go through the process to develop the global stiffness matrix. We need to solve for the global displacements delta. And then after we're done with that process, we can do our back multiplication and get the member end actions F. And then we can figure out what the internal member force P is. So what this lecture covered was steps 1, 2, 9, and 10. And then what the next lecture covers are the intermediate steps 3 through 8. All right, now this is a whole lot to digest. I'll open up for questions now if you guys have them, but I recognize that this is the kind of thing where you need to dive in a little bit and start tinkering with some numbers before you can really develop any meaningful questions. But if you do have a question, feel free to ask at this point before we jump into the next presentation. All right, I do have these presentations canned, which means pre-recorded, and they tend to be a little bit cleaner when I pre-record them than they are when I do them live and in class. So I'll post those for you as well, and that might be helpful to you. So. All right, so here's the second lecture. I call this lecture A2, A for analysis, obviously 2 because it's the second lecture. And so what we're going to do in this lecture is we're going to discuss the steps that I skipped over in the last one. So I skipped steps 3 through 8, and that's basically what we're going to discuss here. As a reminder, in case I give this lecture in a different class than the last one, from our direct stiffness matrix, we want a global stiffness matrix K, we want global displacements delta, we want externally applied loads P, and we're developing a system of equations where we can solve all of those simultaneously. We want K times delta equals P, solve for delta, and then once we know what the delta values are, then we can determine member forces. All right, so the question is, though, how do we get from the element stiffness matrices to the global structure stiffness matrix? How do we get from the K sub i's to the capital K? And so that process is almost universally referred to as the assembly process. And so what we're going to do is we're going to take, for our example truss, we're going to take 7 element stiffness matrices and we're going to assemble them into a global stiffness matrix. We're going to take 7 4x4 element stiffness matrices and we're going to assemble it into one 10x10 global structure stiffness matrix. And so that process is involved because you can't simply add these matrices together. Right? You can't take 7 4x4 matrices, add them together and get a 10x10. You're violating the laws of the universe, and somewhere a black hole will implode upon itself, and no mathematician will ever be happy with that. So we need a process to do this. And what we have to recognize is that these stiffness matrices are intimately correlated with or tied to the degrees of freedom that each of the members or each of the elements connects. So for member A, for example, it connects degrees of freedom 1 and 2 with degrees of freedom 3 and 4. Member B, for example, connects degrees of freedom 1 and 2 with degrees of freedom 5 and 6. And so if we added these 2 element stiffness matrices together, we wouldn't necessarily be violating the laws of the universe for the upper left quadrant, right? Because those correspond to the same degrees of freedom, but for the rest of the matrix, it just wouldn't work out. We would be adding a stiffness coefficient for, say, the 1-3 degree of freedom to a stiffness coefficient for the 1-5 degree of freedom, and that's just not okay. So what we need to do is so here's some language just describing what I just said, that these member A correlates to degrees of freedom 1, 2, 3, and 4, whereas member B correlates to degrees of freedom 1, 2, 5, and 6. So what we need to do is we need to expand each of these member stiffness matrices so that they have the same size as the global stiffness matrix. So what we're going to do is we're going to recognize that with member A, it's not connecting degrees of freedom 5, 6, 7, 8, 9, or 10. So we can expand the stiffness matrix for member A and just put in 0 values for the remaining rows and columns of that stiffness matrix. So we go from K sub A, a 4x4 matrix, to the expanded version of K sub A, which is a 10x10 stiffness matrix. I don't bother to write the zeros in a lot of cases because it just muddies the presentation, and it makes, I think it's more obvious to leave those cells blank than it is to put zeros in there. Now, if we do the same thing with member B, what we're going to find out is that columns 3 and 4 are blank, rows 3 and 4 are blank. And so the expanded version of the element stiffness matrix for member B would look like this. And then so after you expand the 7 element stiffness matrices corresponding to their associated degrees of freedom, then you can add those expanded stiffness matrices together. So what we can do now is add K sub A expanded to K sub B expanded. And when you do that for all 7 of the element stiffness matrices, then you get the global structure stiffness matrix that looks like this. All right, now what does that look like in our spreadsheet? Well, let me look at the PDF first, which is here. And so I think the next page, yeah, so I go through and I write the expanded stiffness matrices. So each one of these expanded matrices is a 10x10. So if we look at the expanded stiffness matrix for member D, for example, it connects degrees of freedom 3 and 4 with degrees of freedom 7 and 8. And so now I can take these 7 expanded stiffness matrices and just add them together using conventional matrix operations, and then I get the global structure stiffness matrix. In this case, since I just did arithmetic in Excel, there are actually zeros in that stiffness matrix. So then the next step, if we're going back to our equation that we want to use, that K times delta is equal to P, write it in matrix notation, then we need to know what the P vector is. We need to know what the vector of applied loads is. So we go back to our structure and we look at the loads that are applied to the structure and we correlate them to our degrees of freedom. Now, we only have 1 point load on the structure. It's applied in the vertical direction at node 3. So it's a load of 22 kips that corresponds with the Y direction. So it's going to be correlated with degree of freedom number 6. But it acts in the opposite direction of what we said degree of freedom 6 is. We said degree of freedom 6 acts in the positive Y direction. So there's a negative value on that magnitude of 22 kips. And then the rest of the elements of our P matrix are 0. All right, so the next step would be to invert the K, invert the stiffness matrix, multiply by the load matrix. But the problem is that if we try to invert our 10 by 10 stiffness matrix now, we're going to get an error because it's a singular matrix. It can't be inverted. And the corresponding structural ramification of that is that we haven't told the stiffness matrix yet which degrees of freedom are restrained. We haven't indicated at all where the supports for the truss are. So what we need to do is we need to restrain that stiffness matrix, and there are basically 3 different ways of doing that. Well, here's a definition here. More specifically, before we restrain it, the global stiffness matrix, it must be positive definite, otherwise the structure is not stable. This is the depth of math that I don't remember, so I have a Wikipedia definition of what a positive definite matrix is. Maybe you guys remember because it's fresher in your mind. Carson, you don't remember that offhand? No, I don't either. Basically, if the determinant of the stiffness matrix is 0, then you won't be able to invert it. And so, yeah, that's one check. That's insufficient, though. You have to check to make sure it's a positive definite matrix. And usually what I'll do is I'll try and invert it in Excel. And when I get an error, I think, oh, shit, I didn't do it right. And then I go back and check for the restraints. All right. So there are basically 3 ways to reflect the restraints on the actual structure in the global stiffness matrix. Now, these 3 methods that I'm about to show you go from easiest to most complex, and they go from the crudest to the most elegant. So the first way is to simply delete the rows and the columns from the stiffness matrix K, the displacement vector delta, and the load vector P that correspond to the restrained degrees of freedom. The second approach is to add sufficiently large stiffnesses to the diagonal elements of K that correspond to the restrained degrees of freedom. And then the third approach is to reorder the rows and columns of K, delta, and P, and we put the unrestrained degrees of freedom first, the free degrees of freedom, and then we put the restrained degrees of freedom last. So, excuse me, given each of these 3 approaches, let's go ahead and look at the first one first. And in this case, if we're just going to delete the rows and the columns of K that correspond to the restraints, then degrees of freedom 1, 2, and 10 should be deleted, right? 1 is restrained by that pin, 2 is restrained by that pin, 10 is restrained by the roller, but 9 is not restrained. So what we do is we go into our global stiffness matrix K, and we basically delete the rows and columns that correspond to the 1, 2, and 10 degrees of freedom. So the resulting matrix is a 7 by 7, and we refer to it as a free stiffness matrix. And the idea there is that the columns of this matrix represent the free or unrestrained degrees of freedom, and the rows of this stiffness matrix also represent the free or the unrestrained degrees of freedom. I got that backwards. It's actually rows first and then columns second. So I screwed that up. Sorry. We also need to do the same thing for the load vector P. So we know degrees of freedom 1, 2, and 10 are restrained. So we delete those from our load vector, and we end up with a 7x1 vector of loads. And then when we go through our solution process, here is the free stiffness matrix. We can invert that and get K inverse. We multiply the inverted stiffness matrix by our load matrix. And ultimately, what we end up with is a matrix of displacements, delta F, that correspond to the free or the unrestrained degrees of freedom. So if we go over here to our PDF, there's the 10x10 stiffness matrix. Here are the three options described briefly. And if we go through and look at the first option right here, then what I've done is deleted the rows 1, 2, and 10, columns 1, 2, and 10. I invert that matrix, multiply by the load matrix, and here's my displacements. Okay, then you can augment this displacement matrix after you go through the solution process and reintroduce rows 1, 2, and 10. And we know by default, if those degrees of freedom are restrained, then the displacements at those degrees of freedom should be 0. Right, so that was option number 1. Let's go back here. What is option number 2? Option number 2 is that we can add sufficiently large stiffnesses to the elements of K that correspond to the restraints. Let me take a second here and remind myself what's coming up. Right, okay, so that's what I thought. So if we go back to our degrees of freedom, let's see here, we'll go to that slide. We know that degree of freedom number 1 is restrained. It doesn't matter how much force we put on it in that direction, that node won't move. I don't know why that won't go. Let's try over here. So degree of freedom 10 is restrained, and no matter how much force we put on it, it won't move. So we can have an F value that is theoretically equal to infinity because that has a stiffness that is infinitely rigid. I didn't say that very well. The stiffness associated with the degree of freedom 10 is infinite. So the same thing goes for degree of freedom number 1 and degree of freedom number 2. So if we go back to our stiffness matrix, then what we can do is add very large stiffnesses to those degrees of freedom. So based on the unrestrained structure, we would have a stiffness coefficient K11 equal to 1154 kips per inch. And if that is a restrained degree of freedom, then that's really going to be infinite, right? So we could go in and say that that is going to be a value of infinity. This is going to be a value of infinity. This is going to be a value of infinity. Well, when you try and write infinity in a computer, it doesn't work out very well. So what you do is you come up with a number that is several orders of magnitude larger than the original value. And then when you go through the solution process, you end up with something that gives you the same end result. So if the original value was 1154 or 619, then we can make the new value would be what, 100 million, 1 times 10 to the 8th. And so 100 million is many orders of magnitude larger than the original value. So in doing that, we would end up with a matrix that is now positive definite. And we can go through and invert this 10x10 matrix and then multiply by our vector of loads to get our displacements. And then so the next question invariably ends up being, well, how do you know when that value is large enough? And that value that you add to it is large enough when you go through this process and you end up with 0 displacements at the end. So we actually went through and multiplied through this. We end up with delta 1 equal to 0, delta 2 equal to 0, delta 10 equal to 0. And because those worked out to be 0 in the end, we know that the magnitude that we added to those stiffness coefficients, K11, K22, and K1010, was large enough. So we can actually go to the spreadsheet in this case. And if we go down here to solution option number 2, you can vary that number. So I could put in a 0 here, and then I get an error when I try and invert the stiffness matrix because I'm adding nothing to the original value. So basically what I'm doing is I'm taking the original value, I'm adding whatever value is in this cell, and I get that. So I can go in here and I could type in, say, 1e to the 4th, And so that's large enough that I can invert the matrix. It makes the matrix positive definite. But look here, I get a non-zero displacement corresponding to degree of freedom 2 and a non-zero displacement corresponding to degree of freedom 10. So those supports are stiff, but they're not infinitely rigid. So we're actually getting a support settlement there, right? I could go in and say 1e to the sixth here instead. Now those displacements are really, really small, 0.00001, but they're still not zero. So if I go in and type in 1e to the eighth, then those displacements are small enough that they don't show up within the precision of my calculations. If I go in here and I expand that a little bit, there's probably a non-zero term there, but we only need to work to 4 or 5 significant digits of precision anyways. All right, so that's how the second method works. All right. The third method is the most complicated, but it's the most elegant and the most useful. I've got about 5 minutes left, so let me go through the theory and then we'll call it to a close for today, and we'll come back and illustrate this on Thursday at the beginning of class. So the third method of restraining the system of equations or restraining the stiffness matrix is to reorder the rows and the columns of K, delta, and P. And we generally put the free or unrestrained degrees of freedom first and the restrained degrees of freedom last. So we can rewrite our global stiffness matrix K as a 4x4 matrix of matrices, right? So each one of those values, K sub FF is a matrix, K sub FR is a matrix, K sub RR is a matrix. And then what we can do is do the same thing for delta, where we have delta free followed by delta R. We have P sub F, P free followed by P sub R, and F is free and R is restrained. And so if we break that out like this, and we expand this using matrix operations, right, then what we're going to do is we're going to multiply this guy by this, and that's going to equal this. We plus this guy by that, right? And so that's what I've done here. I've got this times this plus this times this, right, is equal to that. And so that's just expanding a matrix of matrices multiplied by a vector of vectors to equal a vector of vectors. And so the next step is to solve for our displacements, the free degrees of freedom delta sub F. And so we can do that using these two equations that are shown here, right? If we solve for delta F or delta R in one and then substitute into the other, we can come up with delta F. And it's equal to that. It's equal to the inverse of KFF multiplied by the loads on the free degrees of freedom minus KFR times delta R. And delta R in this case is the displacements that correspond to our supported degrees of freedom, or the displacements corresponding to the restrained degrees of freedom. So in a structure like the truss that we're examining, delta R is usually 0. If the supports are infinitely rigid, we could take delta R equal to 0. And we end up with basically the same matrix operations that we had with method number 1, where we deleted the rows and the columns corresponding to the restrained degrees of freedom. But the genius part of this, if you will, is that now if our displacements delta R are not equal to 0, we can accommodate that into our calculations. So if you go in and want to do an analysis where you have a support settlement, you can accommodate that using this third method, whereas you can't accommodate it using method 1 or 2. All right, anyways, if we take our original stiffness matrix like this, what I'm going to do is reorder the degrees of freedom. So degrees of freedom 1, 2, and 10 go last. So I moved column 1 and 2 to the end. I moved row 1 and 2 to the end. So then I have this guy right here is going to be K sub FF. It's the stiffness matrix that correspond to the free rows and the free columns, or the unrestrained rows and the unrestrained columns. This guy down here is going to be KRR. This guy here, now this is where I need to be careful, free rows and restrained columns. This is going to be restrained rows and free columns. And so we can break those up and we end up with 4 matrices out of our stiffness matrix. And then we can go through our solution process and determine what our displacements delta F are. And then we can go back through and expand that again, and we can solve for the reaction forces. And that's another good part of this is with the method number 3, you can solve for the reaction forces directly using matrix operations instead of having to go through and use equilibrium for each of the members. Right. So in summary, here are the 3 methods. Method 1 is pretty crude. We delete the rows and the columns of the stiffness matrix. Method 2 is just a little less crude. We add sufficiently large stiffnesses to the diagonal elements to the stiffness matrix. And then the third method is to reorder and then go through our expansion of the subdivided stiffness matrix. So we'll summarize at the end with our step-by-step again. So now we have steps 3, 4, 5, and 6 that are included in here as well. All right, so if I had more time, I would go back to the spreadsheet and illustrate these different solution processes. But we're out of time for today. You guys are probably looking at Canvas and you're saying, well, gee, he posted a PDF, but he didn't post the spreadsheet for Excel. Why not? I'd love to have the spreadsheet. And the answer is yes, I know you would love to have the spreadsheet. It would make your homework solution a whole lot easier, but it probably wouldn't make it as meaningful for you. So I'm going to withhold my spreadsheet solution for this example until after you've done at least the first homework assignment on this. And so I'm going to let you guys come up with your own spreadsheet. Yes, it's going to suck a little bit, but you don't build muscles without shedding a little bit of sweat either. So I'll let you guys work through that process, and you'll probably be better for it in the end. All right. I'll stick around for a few minutes if you guys have questions. Otherwise, I'm available tomorrow during office hours or Thursday morning during office hours, or I'll see you on Thursday at 12:30. Thanks a lot.